Last class we went through malloc and free. Achha, I am not going to go through. There are some cousins of malloc, which is calloc and all the realloc. Those are not important. Nobody uses them because whatever we can do with them, you can do with malloc. So there is no need. If you want, you can look up the network and see whether how calloc works. It is just that you allocate array of structures which you can do with malloc by multiplying, and that's what we did last class. So you don't need calloc. Only thing calloc does is it gives you uninitialized memory, initialized memory that makes it 0. But that's not worthwhile learning because mostly we use malloc. So today we get into the concept of the linked list. In the last class, I did talk about the advantages of a linked list vis-a-vis the array. I'll just reiterate that. So we said in an array, everything is contiguous. That's the good part. The obvious advantage of an array is when you go from one element to the next element, it is just contiguous in memory. So just by increasing the index or decreasing the index, you can go to the next element or to the prior element, to the previous element. So that's the easy part. Second advantage of an array is, if you are going to only update data, you are only going to change data, you are not going to add new data, delete data, then array is also a very good data structure because updating means just going to that index, altering some value there. That is easy to do and fast to do with an array. The problem with array starts when you have to insert data in between or you have to delete data from in between. So if you have to insert data in between in an array, you have to waste a lot of time pushing the data which is after that to subsequent locations. That is a slow operation, a very slow operation in fact. Same situation, if you want to delete an in-between record or an element, you have to push all the elements to the left, and that also will take a lot of time. So we said those kind of operations, we don't take much, those kind of operations, array is not a recommended data structure. It is with that in mind that we use a linked list. What is the advantage of a linked list? Very simple advantage or very significant advantage if you will. Thing about a linked list is there is no contiguous allocation. Each node is allocated, another node is allocated, and we just connect them together. They can be allocated anywhere in memory. There is no need for contiguous memory. There isn't contiguous memory in most cases. So you allocate one piece of data here, another piece of data here, third piece of data somewhere else, and what you just need to do is connect those pieces together and you have a linked list. So the disadvantage of a linked list is what? That it's very slow because it's not contiguous. Moving from one to another requires a reference to memory and obviously it will get very slow. So that is a disadvantage. The linked list is slow. In traversal, we call it traversal. Traversal means moving from one node to the next, that's called traversal. Advantage of linked list which I was going to stress was this. If you want to insert an element in between, you can do anytime. You just have to create that element, readjust your pointers, and there you are. That's all you need to do. So adding new elements in between a list is nothing great. You just allocate that node, connect the pointers accordingly, just adjusting the pointers, and you are having that node in between. By the same token, deleting a node is also very easy. Just take that node out, short circuit that node, meaning take the previous guy, connect him to the next guy, take this guy out, and he's out, and free it of course. So that's all you need to take into consideration while deleting a node. Now all this is very easy to say, correct? It's easy to talk. So what we are going to do is, today, we are going to use malloc and free quite a bit. We are going to create a linked list. And I am first going to tell you the structure of a linked list. Then we are going to create a linked list. Then we are going to learn different operations on a linked list. That is adding to a linked list, deleting from a linked list, adding in between somewhere, that is called inserting into a linked list, searching a linked list, These are all going to be interesting operations, and linked list is a very fundamental data structure. It is one of those three that we call the triumvirate data structures: linked list, trees and graphs. So with the modified syllabus, we thought we should cover linked list first, because if you know linked list, that means you know pointers well. If you know pointers well, then we'll have no trouble with graphs or with trees. And if you don't know that well, you'll have trouble all through. So we'll start today with working with linked list. We'll define what is a node in a linked list. We'll see how to allocate that using malloc. When we'll move next, we'll see how instead of malloc, we'll use an interesting operator called new. When we go to C++ or Java, we'll not use malloc. We'll use a slightly more advanced version of malloc called new. It's called NEW, new node, new data. So, but as of now, we'll stick to malloc for creating new data, and we will see how to build a linked list. So let me draw a linked list first, and then we'll see how to create a linked list. So this is how a linked list looks. This is called a node in the linked list. This is another node. Remember, this node and this node may be in two different portions of memory. Remember, these are two distinct portions of memory. They need not be contiguous at all. That's the advantage of a linked list. This could be somewhere else. I mean, I'm just showing from a memory perspective. So each will have some data. Now the data in a node can change from one problem to another. If each node represents an employee, then the data in that will be employee number, employee name, salary, designation, whatever. If each node represents student, for example, the data would be age, gender, college name, could be roll number, could be that kind of data. So when we deal with linked list, we don't worry about what data it is. We worry more about how do you connect, how do you go from one node to another. Each node can be any node that you want. So in classic computer science, without worrying about node, we say the structure of this node is like this. Struct node, like we have been doing so far. We have int data. Now please remember, data can be anything. I mean, data can be, it need not be one data. This itself can be many pieces of data. It could be name, age, gender, whatever. But since we don't want to focus on this part, whatever the data may be, that's not important. That is changes from application to application. This may be one field or these may be several fields. We are really not bothered, because from the treatment of linked list, it is immaterial what data you have. What is important is how do you create a link to the next node, and how do you define that in a structure. So this is what you use: struct node star next. Okay. This is crucial. So struct node for us consists of, as we recognize, all the data we have fused into data, let's say. Okay. And the important thing is this guy. He is a pointer to the next, always or generally called next. Okay. See how he is declared. This is also called, in computer science they make a big show out of it. This is called a self-referential data structure. By the way, why it's called self-referential, though wrong, is because it has a pointer to a node like itself, not itself. That will become a self-pointer. So it has a node. So in this case, what is the structure of this node? This is also a struct node only. So this next is used to point to this node, not to the current node. So in order to create a pointer to this node, we have a struct node star next. And from here we have a pointer to this node. And we have a pointer to this node. And the last pointers next, obviously, the last pointers next will not go anywhere. Where will it go? It will be null. Okay. Null, as in null. Nothing. So that will be the last. That is how you make out that you have reached the end of the list. Otherwise, how will you know you have reached the end of the list? That means we have reached a node whose next is null. That means it signifies the end of the list. So normally we refer to it as this guy as the tail of the list. Tail is not very important because you can always get to the tail. But what is important and what is stored normally is the head of the list. So this is called the head of the list. So always you can create first the head of the list and then you keep creating each node as you go. Now it depends on how you grow the list. Is everybody clear so far what is the linked list? Because this I had briefly alluded to in the last class also. So this is a linked list. Now how do you add nodes to a list? There can be two ways. This could be the first when the list is empty. Now how do you know the list is empty? The head is null. That means the list has nothing in it. This is the first time that something is going to get created on the list. So if head is equal null, what it means is, because head represents the head of the list, if that itself is null, it means that there is nothing in the list, right? It is empty. Then we create the first node. Anyway, we create the first node and we put some data in that. Let's say some data 50. And when we first create a node, we ensure that its next is null. That its data is 50 and its next is null. Now you'll ask why? Because whenever you create a node, we don't know this node is going to point to somebody or not. We don't know. And so it's always safer whenever you create a node, whenever you allocate memory of a node, to make its next as null. Because if I want somebody coming up, then I'll connect it. But when a node is created by itself, I would create it with the next as null, because that is standard. And then, depending on requirement, I would connect it to the next node or whatever. Okay. So this is what I would do. Then, so only the first time the head is going to be null. Now if you want to add a next node, question is whether you want to add it here, that is grow the head, grow the list like this, or you want to grow the list like this. Okay? It is up to you. Some people prefer growing the list like this, some people prefer growing the list like this. Unless some specific order has been specified, you have free choice as to how to add the nodes to the list. Unless somebody says, no, this is the way it has to be done. Somebody says there has to be a LIFO order or a FIFO order. We'll discuss all of that. If nobody says what is the order, it's up to you. So what we are going to do is, if the next node which is going to be added in the list is going to be, let's say, 35, then I am going to create this node, its next point to this node, that is the previous head, and I am going to make this guy the new head. Okay, I'll repeat this. When I create the first node, when head is empty, that is when I create the first node. When I create the first node, I allocate it, I make its next as null, and I allocate the data. I assign the data. So I will have at that point just this node, right? When I have only one node. When I add a subsequent node to the list, what I am going to do? I am going to say that I am going to create this node. I have to create this node. Put its data as whatever data you ask me to, 35. But I am going to play a little game with the next. I am going to make the next equal to this node. I am going to make this next equal to this node. Or rather, I am going to make the next point to this node, not equal to this node. I am going to make this next point to this node, because then I am building a chain. And my head is also going to alter. My head is going to become this. So a new head is going to be returned every time I add a node. The head is going to change. And the function which adds a node is going to give me a new head pointer. Does everyone understand why I am getting a new head pointer? Because I am creating a new head every time. I am adding to the head. So if I now add yet another node, let's say 38, what I am going to do? I am going to say this way, data is 38 and the next is going to be this guy, and now this is going to become the head. So this is going to be the head, and we are going to have 3 nodes in the list at this point. And as you can see, the last node will always have its next as null. So that is how we will know that we have reached the end of the list. Okay. So this is the basic operation. Now I am going to go really slow and do it programmatically. I'm going to build what I have just showed you, step by step, and just watch how are we going to do it, because it's super important that you understand. Some of you will get it right away, excellent. Some of you will get it over time, some of you will never get it. Okay? So, it is also healthy. Okay, so we will start with some practice question. We will start as usual our STD lib or STDIO. We will also include, because we are doing malloc and all, we will also include std lib.h. Now, let me add functions for add node. So I am going to define some variables which are going to be outside of main. So they are called, in a way, external variables or global variables. We will have a discussion on this soon. I am going to create a variable here called called struct node first. First I am going to create that data structure. Struct node, which represents one node in the linked list. So struct node, it has, as I said, two data members. First data member is always we are taking as int data, just one data. It may be 4 or 5 fields representing one employee or one student or one customer, could be anything. So int data, right now we are keeping it as an opaque int data. The second field is important. So struct node star next. So the field next is a pointer to a node. It is going to be used to point to the next node in the list. Is it okay? It's going to be used to point to the next node in the list. And the last node is going to have its next as null to signify that it's the end of the list. Okay. So this is how I would declare a node data structure. Is everybody with me on this? Two fields, one is data, one is node pointer to the next node. Everybody clear why I am designing it like this? Okay, now I am going to keep one more variable outside main. What is the beauty of keeping variables outside main? They can be accessed in main also, and they can be accessed in other functions also. They are called global variables. So I am going to create a global variable. We have not discussed this at length because I have to show you how global variables work, how static works, how automatic works, how register works. We will come to that. Okay, but let's get this in order and then we'll discuss that. That is just data, information. We will create a variable here called the head pointer. How do you think I should declare the head pointer? It's a pointer to a node, right? So how will I create it? I'll say struct node star head equal to none. Do you know why I am doing this? No, yes. Because right now nothing is there on the list, so head will be null. So we start the program with head equal to null, as it should be, correct? So struct node star head equal to null. Now we start writing. Okay. Now this session is going to be a little heavy, so bear with me. Okay. Because there is going to be a bit of pointer manipulation, and if you have been following me so far, it's going to be easy, but otherwise it's a little difficult. Okay. Now I have created the head node and I have initialized it to null. Everybody with me on this? Yes? Now, I am going to not write main yet. I am going to write instead a function called add node, which adds a node to a list. List is represented by head. It is going to add a node to the list and potentially it is going to give a new head. Obviously it will give a new head because the way we are adding is we are adding it to the head again and again and updating our head every time we add, correct? So I am going to create a function. It will give a node pointer back. Please look at it carefully. Struct node star. Now let's go line by line. Okay, now watch every line that I write. Please understand the meaning. Now add node means, think, what am I going to do? I am going to create a fresh node and add that node to the head of the list. That is, this node's next is going to become the previous list head. I am going to connect it to the head of the list and make this guy the new head. This is what I am going to do. But I have a special case. Okay, but we'll come to the special case later, where head itself is null. It doesn't matter. We'll handle it. So my first job in add node is to create a fresh node whose data is equal to D and whose next is equal to null. Then I will connect it the way I want it. Are you with me? I'll first create a new node. I will cause a new node to be created in using malloc. I'll create memory for this new node. After that, I'll initialize that memory accordingly for my problem, and then I will use it for connecting it to head. Okay? Watch carefully. Now I am creating the first node, creating one node, not first node, but creating, in this case, first node, but add node always is used to create a node. So I am declaring a temporary pointer, struct node star. I am just declaring one pointer. You will realize why I am doing it. Okay? Then I am going to say temp, watch this line. I will make a bit of a malloc. Temp is equal to malloc. Remember, I have to allocate memory for that node. Temp is equal to malloc. Can you complete that? Size of what? Size of struct node. I am going to create a new node. So the amount of memory I need to allocate is struct node. So size of struct node, I am allocating that much memory. Now malloc will create that memory. Again, I am not going to waste my time. I am not going to check whether malloc works correctly or not. Malloc may sometimes give you null, I told you. When will it give you null? Left. But we will not worry about it. But when you write code, real life, please check. Okay? It's irritating. This is the problem of C, that after every line you need to check whether that line worked or not. What this results in is called khichdi code. Khichdi, you know? Okay. It becomes like noodles, mixed, intermingled. Now we will correct it when we go to Java or C++, whatever comes next. This kind of irritating thing which you need to do, that is after every line check whether that line worked or not. That is called pessimistic programming. You shouldn't do that. There is a way to get out of it, but not in C. C is an ugly language. So what I am doing, I am skipping it altogether. I am assuming what is called as a sunny day scenario, which says malloc means I will get memory. Don't worry about not getting memory. Okay. Now, if you see the malloc call, something is missing in my malloc call. Remember? Malloc returns a void pointer. And what kind of pointer am I seeking? I am not seeking a void pointer. What am I seeking? I am seeking a struct node star. Are we clear? So what will I do? That malloc, I will cast it into struct node star. As I told you on that line 11, there is a bug because malloc returns a void pointer and I don't want a void pointer, remember? I want what kind of pointer? Node pointer or struct node pointer. How do I do that? What should I say? In the bracket, what should I say? Struct node star, because I want a node pointer. So how do I get a node pointer? I say struct node star malloc. Yeah, I am hoping everybody have understood this line. Is this line clear? What am I doing? I am allocating a node memory and getting a proper pointer to it. Because I can't get a void pointer. Void pointer I won't be able to work with it. I am creating a node pointer, or I am casting it into a node pointer. That thing which happens within that left side bracket is called a struct node star. Okay. So we have this struct node star pointer, we cast it. So we have temp is equal to, we have converted that into we have allocated a pointer. Now we should immediately change it to temp data should be equal to D, because temp has two pieces. Remember, any node has two pieces. What are the two pieces? Data and next. So by standard practice, whenever I create a node, I will make that assignment. So I will say temp data, temp's data. It's a pointer, so I can refer to data by saying arrow data. is equal to D. Temps data is equal to D. And then I will say temps next equal to null. I will blindly make it null because that is how I initialize a node data structure. Is everybody with me on this? I have created a node, I have allocated memory for a node. The node now contains data and temps next is made null. I will do it every time. Now comes the actual part of the code. Okay. Now I update my head if this happens to be the first node to be created. Correct? Or it will happen every time also. So I will say if head equal null. That is how I know that this is the first node which is getting added. So head, if head equal null, then I will say head is equal to. That means there is nothing in the list yet. This is absolutely the first guy to get into the list. I have created him, I have checked whether the head is null, and if the head happens to be null, then head should be this guy. Correct? Head is a pointer to the first node, so head should become this guy. So I will say head equal to, what should I say? Wait. Temp. No, yes. I should say head is equal to temp because I created temp, I initialized it accordingly, and now I have to say because the head list is empty, this guy who got just created is going to become the head of the list. So I am going to say head is equal to temp. Done. End of the story. Correct? Yes, no. Okay. Else. Now I am writing it and then we will go through it again. Else. Else means what? The head is not null. So can you imagine, please imagine in your mind, that head is not null means there is some list already. And I am going to put a node ahead of that list. I am going to put a node. Head is not null means just imagine some list is there. I don't care what that list is. There is some list. And I have to add a new node to that list. So how will I add a new node to that list? We said we are going to always add at the head. So what will I say now? Temps next I have to change. Temps next. Temp already has data. Its next is right now null. But since I am adding this guy to the head of the list, I will say temps next equal to, beautiful. Temps next is equal to head, earlier head. There is already head. I create a new node. Look at my hands. I have a node. I have a head, some list. I am creating a new node. I want to make this guy is next equal to this guy. So which means what? My next is the old head. My new node's next is going to become the old head. I am adding to the head. It becomes easier. Okay. Let me ask you now. Return. Next line. Now I have to do one more. Anyone? I have made temps next equal to prior head. I need one more line. Just one line. No. Something to do with head, but what should I say? I have said temps next is equal to head. I did that already. What should I do more? What happens to the head? Head equal to temp. Head equal to temp, no. Head equal to temp. All of you agree? No. See, there was a head already. I'll draw it. Head was there already. Then I created a fresh node. I have to connect this fresh node to the head. So I said temps next equal to head. Should my head change or not? Who is my head now? This guy, no? So I should say head equal to temp. So if you want a pictorial or a graphical description, so to give you the picture, this is what I had, let's say. Some kind of list existed because head is not null. I don't care what existed, but let's say this is head. This is head. Now I am creating a new node. This is a new node I am creating. I have allocated memory. I have put data in it. Right now its next is null, but I want to change it obviously. So what I have to do? His next should become this head. How did I do that? This new node is temp. So I said temp's next equal to head. Head is a pointer. Next is also a pointer. So temp's next. Temp is also a pointer. Temp points to this node. This is temp. This is temp. So temp's next equal to head. I have to do that to get this guy ahead of this guy. The old head. This guy is the old head. He's there. And I am now connecting my next to him. And what I have to do? I have to update my head, or rather not my head, but head of the list will now become this guy, isn't it? After this operation has been done, who is the head? This guy is no longer the head, no? This guy is the head. So head is equal to temp. So I will say head equal to temp. So we will go through add node again. And we will write one line and then we will go through it again. Okay. So we will say after this else, now what should we return? We should return head. Always when you add things, you should return the head. Because head is the list. The new list has changed. Whenever you refer to a list, you refer to the head of the list. So return head. It may be the old head or a new head. In this case, it will be always a new head. Okay, now let's walk through it again. Add node. So let's look at add node again. Add node, see the signature. Add node is a function. It takes one data as a parameter, d as a parameter, and it is expected to give back a node pointer. It is supposed to return a node pointer. So that indicates how I have created it. So I am saying struct node star add node and whatever parameter it needs, which is int d, you can call it whatever you want. Now let's look at the body of the function. Line 10, struct node start temp. So I am just defining temp as a node pointer because everything we are dealing with is in pointers. So we are just creating temp as a temporary pointer. It points right now nowhere. Then look at line 11. Now, since we have to add a fresh node, I have to create that fresh node. Automatically nodes don't get created. I have to create it. I have to allocate memory to it. What is the way I allocate memory? I say malloc. That is the standard way of allocating memory. I say malloc. Malloc asks you, I'll create memory, but how much memory should I create? So I tell it, how much memory should you create? Big enough to hold a struct node, because I need memory for this node which is getting created. So I ask malloc size of struct node, that much memory I want. Malloc says, I'll give you a pointer, it's going to be a void pointer. You cast it the way you want it. So that's why I applied a casting. I converted whatever malloc gave into a struct node star. It gave me that node pointer. Now, temp has become a node pointer properly. Earlier it was only declared as a pointer. It didn't have anything pointing to it. Now it has some piece of memory pointing to it. Earlier temp was just a pointer. What will you do with a pointer? It has to point to something. Now it is pointing to a node, a element, which has two parts, next and data. So now, soon after malloc has been allocated, line 12, I am filling up that data structure, which I just got created. Temp's data, that field data, is equal to d. That is what I got as a parameter. I said temp data is equal to d over. Then I said, since it's a freshly created memory, by default its next, let it be null. I will change it if required. Next is null. Okay. I made next null. So that is how a new node was given birth. This is how any node takes birth in a program. Right? We allocate it, we initialize it. Later, as we go to C++ and Java, this allocating memory and initializing it will be collapsed into one step. But C doesn't permit us to do this in one step. We have to do as many steps as needed. First we have to allocate memory, then we have to initialize the memory. You see, line 11 is allocating the memory, line 12 and line 13 are setting it to some credible values. Correct? So once line 12 and line 13 are over, I have got a node and I have got temp pointing to that node of initialized memory with data as there and next as null at the moment. Now I am going to see how to add this chap temp to the head of the list. Now two situations present themselves. Correct? One situation is head itself is null. If head is null, that means this guy is the first guy on the list. There is no head. That is why head is null. So this guy is the first guy on the list. So what do I do in that case? If head equal to null, my answer is trivial or my job is trivial. I simply say, since anyway there is nothing on the list, Mr. Temp, you are now designated as the head. There is nobody. So you are going to become the head. You are the first guy who is visible. There is nobody else. So head is null. Nothing is there on the list. So Mr. Temp, you are now the head. So head equal to temp. Over. Else means what? Head is not null. That means there is already existing list on top of which I have to add this temp guy. So there is already a list, some list. That list is starting node is head. I know that because head is supposed to store that. So now what am I doing? I go into the else part. Now there is a head and there is a temp. That head has some list. It may be 1 node, 2 nodes or 20 nodes. It doesn't matter. So there is some head and there is some temp. Temp is what I have created just now, new node. And there is a head which points to the existing list. What do I have to do now? Temps next should become that guy. That is temps next should go to the head, earlier head. Because otherwise temp will not come into the picture. So temps next should become head and the new head should be now temp. Because now this guys, the list starts here. The list starts with the temp. So I am saying head equal to temp. And after all this is over, I am returning the new head to the column. So add node will give the new head to the column. Okay. So that's how this head will keep changing. Okay. Now it will take, I am doing very simple stuff first. This is called adding a node to a list. Okay, so what we are going to do is, we are going to play with it a little in main. Okay, and observe something. We are going to write some code with that list, very simple code, and let's see how it goes. Okay, so I am not going to add another function yet to delete or to search or anything. Let's keep it very simple and straight. There is only add node. So how do I build a list? What is a list that I am going to build? Okay, let's say tentatively my list is going to be, finally I want to build a list like this, 10, 20, need not be any ascending order or anything, 15 and something, and my head should be this. That is, after I have done the job, my list, let's say tentatively, should be this. How am I going to build it? Are you with me? We are going to build this list using the add node which we just wrote. We are going to craft this list piece by piece. Okay. Shall we start? Okay. Now, how do we start? Okay, let us go back to the picture again. Just, who do I build first? Should I build from 10 first or 5 first? 5. Because remember, I am adding always to the head. I have to add one by one to the head. Remember, and the previous head, this guy becomes a new head and points to the previous head. We just saw that logic for add node. So, and head is a global variable, so it's always available. Okay, so we are first going to build 5, then 15, then 20, then 10. Okay, and then we are going to check whether we built it successfully or not. Okay, that's all we are going to do. Let's do one at a time. Let's go back to our main. Okay, so what I'm going to do? So I'm going to declare a pointer temp for the sake of declaring it. Node star, struct node star, T. I'm just calling it T. Okay. Now, watch carefully. I'm going to say, I'm going to create the first node. We said the first node we are going to create is 5. Okay. So, we are going to say T is equal to add node 5. Okay. Now, let's step back a little. Just let's understand what has happened. What happened? Right now, head was null. Remember? Why is head null? Because if you go back, go up. Oh, I created. Line 8, head is always null to start with. Are you with me? So, now, come to the line that we are doing. T is equal to add node of 5. So, what it will do is, it will create a new node with the data as 5, with the next as null. Yes. Remember, whenever you create a new node, data is 5, whatever data you give, and the next is null. So you will get a new node created. And right now head will be null. Agreed? So because head is null, that head, okay, will be returned as the return value. So T at this stage will contain the head. So if you see what is T, T is whatever add node returned. Add node returned what? A pointer to the first node, which we are going to call as head. So head got updated to T. To whatever the node which got created. And that is also available in T. So because of add node, head also gets updated, and because the return value is there in T, T also contains head. Both these variables contain head. Okay. Now I am going to add another node. So I am going to say again, okay, I think we are maybe confusing you by saying T equal to. Okay, let's just blindly do, because that anyway head is getting updated. So I have it in the head. First line also you can remove. Keep that declaration there, we'll need it. Okay. Add node 15. Then 20. Then 10. Okay. The return is not being used, that's okay, because head is getting updated, and then later we'll comment on it, but not now. Okay. So, again, because this is the first time, I am going a little slow. Add node 5, at that time, head was null. When I executed line 28, head was null. Do all of you agree? Because the first time the node was getting created. At line 28, a new node was created and head was pointing to that node. Then on line 29, again a new node was created called 15. Let's call it 15. 15's next was made to point to the old head, which was 5's pointer, and the new head became pointing to 15. The new head was pointing to 15, at that point on line 29. By similar argument, on line 30, there was already an head which was pointing to 15 and 5, that is the list was 15 and 5. Then 20 came along, 20 was created, and 20's next was made to point to 15, because 15 was the old head. So old head was 15, new head is 20. So at line 30, after line 30, if I ask what is the head, that will be 20. 20 connected to 15, connected to 5. Then when I added 10, then what happened? A new node 10 was created. 10's next was pointing to 15. 20. And 10 became the new head. New node was created. 10's next was pointing to that 20 node, and 10 became the new head. So, just to depict it, how did this all transpire? What happened first? I'm just showing this. First we created 5, and at that point my head was this, first node, head became updated. Then I created 15, and this was originally temp, remember? This was temp. And temp's next was made head. Okay, this happened. And then head was updated. Okay. Head was updated to point to this. When these two happened. When I added 20, again temp was pointing here, new node. 20 was created here, and this guy's next was created here to the old head, and this guy became the new head at that point. So these guys are no longer heads. This guy became it. Then when I added 10, this was first temp. Temp's next became 20, and this head, we made this guy the head. So currently it is like this. Head is here. Okay. 10, 20, 15 and 5. This is how it is. I don't know how many of you understood this. So it's not that difficult if you think a little. So the first node in our list is 10, points now to 20, because we are always adding at the head. We are always going forward. The list is going forward. So we have 10, then 20, then 15, then 5. This is how the list was created. This is how the list is built. Now, having built this list this way, what comes next? Okay. Now, just to check whether this list is working, I am going to write a small function called display. Display will do what? It will start from the head of the list and display all the elements of the list by what is called traversing the list. It will traverse the list. Traversing the list means going through the list. Some people call it traversing, some people call it crawling. If you know swimming, you know there is a crawl where you take the one hand down and take the next hand up. So the crawling in the list, or just going forward in the list. We will start from the head and go up to the tail. Who is on the tail? Tail is 5. Or tail is null. Tail is always null in that sense. But tail we call it as 5, whose next is null. Okay, that is how we say. Now, I am going to write a small code which will traverse the list and display the list. I can write it as a function, or I can write it as just a code. Let's write it just as a code, then we'll put it in a function. So a display code right here in main. Can you come down? Yeah. Okay. So I'm going to use that T now, which I have there. I'm going to say T, or I can write a for loop also, or a while loop also. So let's write a for loop. Okay. So I am going to use that T for T equal to head. Okay. Now semicolon. Yeah, please understand the impact, because you are now going to traverse to the list. Okay. You have to try and understand each line. Does T equal to head make sense? No, yes. So T, which is just a pointer, I am equating it to head. So T is head. Can you imagine? I am at with T I am sitting on the head of the list. Now, what will I do? How long should I go on printing? Till this T is not null. If it is null, then I can't print. You are with me? Till it becomes null, I can print whatever data is there in T. So, while T not equal to null. Next, wait. Now, after I display every node, what should happen to T? Very good. See, I am going from the beginning. First T is going to sit at the head. How long am I going to go on working with this T? Till T hits a null. That is the last node of the list. Beyond the last node. How am I going to... See, normally in an array, how do I move forward? I say the index I, whatever index you are using, I say I plus plus, or I say I equal to I plus 1. That is how you move in an array. By now you know how to move in that array. Right? I equal to I plus 1, that will, and then you say array of I, or on the next element. Here, that happens when the memory is contiguous. You can just move I equal to I plus 1, the next piece of data is at the next index. That is not how a linked list is going to work. There is nothing at the next, it's not there. It's only chunks of memory allocated separately all over the memory space, right? So, how am I going to go to the next guy? The only way is to the pointer. So that is how I am not going to say I equal to I plus 1. It won't take me anywhere. But this T, if he follows that next guy, that is T becomes, T is next, then T will have the data. We'll start with the head of the list. Then we'll continue till T crosses the last, which is T is not equal to null. We'll continue in that for loop. And the last line is the important one. Every time, after you are done with one node, you have to look at the next node. So how do you go to the next node from first node? You say T is equal to, T is next. Because they are pointers, you have to accordingly use it. So T is equal to, T is next. Okay. So T is equal to head, T not equal to null, and T is equal to T is next. That is how the pointer crawls forward. First it is at head. Every time it is checking whether I have reached null or not. If I have not reached null, I do something, and then at the end of the for loop, automatically the last thing happens. The last clause is executed, which is T is equal to T is next. So what should happen in the body of the for loop? I should display the data, isn't it? Maybe one line at one item. So I will say printf percentage %d T is data. T is a pointer. So how do I get to the data of T? T is arrow data. That's it. So now have you got it? For loop, we start from the beginning. T equal to head. Always we start at the head. Then we will say T is equal to, how long will I go on? Till T has hit null, T not equal to null, till then I am in that. What will I do after every step? T is equal to T is next. That is how I crawl forward. Once I display the data in the first node, at the end of it, I say T is equal to T is next. Always checking whether it has reached null or not. So now, if I run this program, let's see what I get. What should I get? I should get from the head. That is, first I should get 20, 10, 15 and 5. Correct? It's in that order. After that percentage D, we will see that on a different line, otherwise it will all come jumbled. Yeah, let's run it and see what we get. Yeah, as you can see, this is how the list looks. It is 10 at the head of the list, 20, whatever, 15 and 5. Okay. So that's how the list gets printed and get displayed. So I want the answer to be 60. Did you get the question? I want the sum of all elements in the list. You always have the head. You always have to start from the head. How much is the sum of all elements? Do it and tell me. I want the sum. Again you have to start from the head. Very simple. 2-line answer. Over. Good. Just the sum of elements in the list. I am just saying, show me the sum of elements in the linked list. I have already shown you how to display elements in a linked list. Okay. Yeah, some of you are doing it. Same way as you did display. Only thing is you create a variable sum. What do? Again start from the head. Go up to end, which is t not equal to null. And then every time crawl to the next node and take the value and add it into sum. So let's write it. Create a sum. Int sum equal to 0. Okay. Int sum equal to 0. Then I am going down. I am writing the loop again. I am going to use the same t. Okay. If you want, create another t, but no use. Okay. For t, again same loop, no? For t equal to head, that is start from head. T equal to head, that is the initial condition. For t is equal to head again. Same condition, t not equal to null, and crawling forward, t equal to t is next. Only variation is, we say sum is equal to sum plus t of data. We don't want to display data, we want to accumulate it into sum. And then print with a print sum is equal to percentage d backslash n sum. Done. Yeah, so we are done with sum. So sum is equal to 50. Is it 50? Sum is equal to 50. No, that's not magic. We're just going through each value, each node, picking up its data, adding it to sum. That's all we are doing. Okay. Now, I am stopping here for now.